Okay, I think we're live. All right. After again, I've been kind of obsessed with fractal geometry. I'm reading this book called Introducing Fractal Geometry, and there's the face of Benoit Mandelbrot, the father of fractal geometry. This time, I'm gonna attempt to, well, having already made the Sierpinski triangle, as you see here, using this dice throwing method, which basically an iterative randomized method. I flipped to the next page of the book, and I realized that, oops, wrong window. I flipped to the next page of the book. Sorry again, and I realized that, by the way, this random algorithm for the Sierpinski triangle, the random method of generating the Sierpinski triangle was discovered by Michael Barnsley. But Michael Barnsley also discovered that you could tweak the algorithm to make it generate any type of fractal. And in particular, you can actually generate this Fern tree using a similar iterative algorithm. I really like this Fern tree, so I'm gonna try to generate it. This book didn't give me the algorithm, but I did a Google search and I found this. Now, this description of an algorithm is very short, so I hope there isn't any missing important details that I'm not aware of, but I'm just gonna guess. What this means is you're gonna start with the coordinate position x and y equal to 0, and then you're gonna throw a die, sort of, it's just a six-sided die won't work, so you're just gonna generate a random number, and then 1% of the time, based on the random number, you want one of these four conditions to happen, and you want 1% of the time to iterate in this way. And in this way means you want to update the value of both x and y based on this equation. This xn plus 1, that just means the next value of x, I believe. So this is saying the next value of x we want is 0. Yeah, I have no idea how to sort of intuitively visualize or understand this algorithm. I guess I just have to code it and hope for the best. So, all right, let's do it. So I'm just gonna start from where I left off with the Sierpinski triangle code. I'm gonna rename this to the Barnsley Fern. Use the same canvas, and I think I'll keep the plot function because that will allow me to see the point, and I will keep this button, which every time I click the button I can do one single step. I'll keep the definition of what point is, but I don't need 3 points. I'm gonna redefine the step function to do a different thing. So I'm gonna gut this thing. And this counter, we'll need like a loop like this. For now, I'm not gonna have a loop. So I'm gonna try to faithfully follow the instructions of the algorithm over here that we see on the left hand side and write it in terms of JavaScript or TypeScript, whichever you like to think of this as. So I'll say the point, which includes x and y. The point is 0 and 0. That's the starting point. And then for each step, I'm gonna get a dice roll. Probably we should not call it a dice roll. I'll pretend it's a 100-sided dice roll. How about that? So if the dice roll 100-sided dice, I'm not even, it's actually a continuous dice. I'm not even gonna math.floor it or anything like that. I'm just gonna say if the dice roll is less than 0.01, which that should happen with 1% of probability, then I want to update the point such that the next x value is 0 and the next y value is the previous y value times 0.16. Right now I'm kind of thinking just using this point construct is actually making it a little harder to read the code, so I'm not even gonna do this. I'm just gonna make an x variable and a y variable and get rid of this point construct. I think this makes the code easier to read with respect and easier to relate to the algorithm as it is described. Excuse me. Okay. So then I can serve. This code looks more like what is written here, this way. Okay. All right. So this is saying the next iteration, the yn plus 1, the next iteration of yn will be 0.16 times the previous y. Okay, and then now else if the dice roll with 80% of the probability, 85, sorry, which will be I want to use the 0.1 as the offset, so maybe this would be equal, I'm not sure. So 85 plus 1 is plus plus 1 of the probability, so that's, I'm gonna use 86 as the offset with that amount of probability, or with that condition. I'm gonna say the x is equal to 0.85 times x plus 0.04 times y, and y is going to be negative 0.04 times x plus 0.85 times y plus 1.6. Wow, how does this work? I really would like to read an explanation of how this works, but I'm a little worried that once I attempt to read that paper, I wouldn't understand anything on there. I still want to try though. Okay, so I'm gonna add 7 to 86, which is gonna get me 94, 0.94 as this cutoff point, and then so for the condition F3, the new x is going to be 0.2 times x minus 0.26 times y, and the new y is going to be 0.23 times x plus 0.22 times y plus 1.6, and then finally for the remaining of the time, the new x is going to be negative 0.15 times x plus 0.2x times y, and the new y is going to be 0.26 times x plus 0.24 times y plus 0.44. This is not an equal sign, but it's a minus sign over here. And okay, and then once I have this new dimension, I'm gonna plot this thing. Okay. Maybe I should check my math. Check if I copied things over correctly. Okay. Yes, that looks like what he wrote. That looks like what he wrote. And yes, this looks like what he wrote. This looks like what he wrote. And then in terms of the probabilities, like 1% of the time, and then 85% of the time. So add that to 1%, and 86 plus 7 is 94. No, it's not. 86 plus 7 is 93. Yeah. I can't do math. Okay, let's see what happens. I have no idea what's gonna happen. So I'm gonna step. I have a feeling, okay, all the plotting is going on here. I have a feeling maybe this is like, I may need to scale this baby up. So maybe this is meant to be scaled up into the range of some range. What I'm gonna do is just take a look at the maybe use console.log to take a look at these x's and y's to get a sense of the range of these numbers. And then I sort of scale them up when I'm plotting them. I can just do the scaling in the plot function. And that way I don't mess with any of the actual math if I do it there. Okay, let me see. So number get as big as 8 and 9. Oh, the number does go negative some of the time. But most of the time it stays between 0 and 10, I feel like. But we should probably represent the negative cases. Sometimes it goes to negative. Okay. Huh. That's interesting. I'm just gonna scale it to, how should I scale it? I guess I can, let's just try scale it by 10 for now. So I'll say scaled x is x times 10. Scaled y is y times 10 for now. We might have to tweak this. I have some negative numbers, right? Maybe also offset it like plus 2 after scaling it and add an offset to it. Okay. I'm gonna try to do it a lot of times now. it shouldn't print out the coordinate. We'll probably let it go faster if I didn't console that log. I'm gonna give up on this and close this tab and start another one. Oh, dang. That's a Fern. It works. Okay, I'm gonna, oh, by the way, if you don't know how to close a process in Chrome, you go to this triple dot menu, go to more tools, task manager. I'm gonna try to close out that. Yeah, I killed it. Okay, but I do get a Fern here, and that's quite more, maybe 3 times more in both directions, maybe. Oh wow. Okay, I want to move it over even more than 15. Maybe scale it even a little bit more in the Y direction, in both directions. Oh, such beautiful beauty. Such beautiful beauty. Wait, am I doing this right? Doesn't seem to be having an effect, my offsetting code. This is X, right? Am I even successfully? Oh, I need to increase it by a lot more. There. Okay, maybe flip it over. Flip it in the Y direction, maybe. Oh, the offsetting doesn't even need to happen in the Y direction, I would say. Okay, wow. I'm gonna flip it in the Y direction so that the tree is right side up. No, that totally doesn't work because I need to, if I'm gonna flip it, I need to add the height of the canvas. There's our Fern. Wow, that's beautiful. That's beautiful. I'm gonna try to make it a little more beautiful by making it green, perhaps. How do you make it green? ctx.fill style, I think. Green. Is this how you do it? Yeah. Okay. Wow, that's incredible. That's incredible that I mean, I have no idea how this randomized algorithm works. I guess there's also one aspect of this, which is that you can keep zooming in to this supposedly to get more detail. But in order to get more detail, you have to do many more iterations though. So it doesn't come freely. It's not like, so like every time you try to zoom in more to get more detail, you just have to calculate so much longer to get that detail. So it might like take a while. 0 to 50 for green, maybe 0.7 for the alpha. Does that work? Does it give it like I don't feel like that helped. Okay, well, in any case, that's the barn tree. This is a much more vivid rendering of it, and probably with more iterations. Than mine. It doesn't look quite the same as mine, I must say. What did I do differently? Maybe I did something wrong, I have to say. Maybe, or it could be the quantization errors with the double floating point numbers. I don't know what exactly, why my picture doesn't look exactly like the picture on the website. If you know the answer, please let me know. But yeah, I think I'll stop the stream here. This was a fun exercise, and I encourage you to try to do the same and hopefully get a better result than I did.